All right, 2010. We're just going to do one question on this video. Can you solve a graph question given in a free response? Do you understand the area, area above, area below, derivative at a point, and what they're asking you to do? So the function g is given, defined, and differentiable on this. So first thing I look at is this is g prime. This is a derivative graph of g. And you're given a value for g at 0. That's a starting value. And it asks you, can you find g at 3 or g at -2? So what's the setup when you're given a point and you have to find another point in calculus? So what's the y coordinate? We set it up. It's 5 plus, and then we integrate the derivative. So we're going to integrate starting at the bottom bound, what we started with, which is 0. And then we go to what I'm looking for. So in this case, the first one I'm looking for is 3, and that's the setup that I'm going to use for both. So I'm going to switch from here. Again, I'm going to call this, again, this is 2010. Long time ago, right? So, calculus has been around for a long time, even past 2010. So number 5, we said the setup. We start with 5, and then we integrate the derivative from 0 to what I'm looking for. So the first one was 3. So there's the setup. Now, off the graph, I need to find the area from 0 to 3. So if I look from 0 to 3, what do I see? So that's 0 to 3. So first of all, 0 to 2 is a quarter circle. So I need to know the area of that quarter circle and to know it's above. So it's positive. So the radius is 2. So I do a quarter circle. And then I have a triangle I'm going to add on to that, which is half the base times the height. All right, so let's put that together. So first the quarter circle, pi r squared, and the radius is 2, divided quarter, divided by 4, and then the triangle, half the base times the height. I'm not going to simplify it until I have to simplify it. I don't have to simplify it in part A. -2, same setup. 5 plus integrate from 0 to what I'm looking for, which is -2. And again, I'm going to integrate the derivative, which is find the area off the graph. So I do notice here is the bottom number is bigger than the top bound. So I'm going to start with the negative parentheses and just find the area I'm looking for to make it simple. So from 0 to -2, find the eraser, get rid of this. So 0 to -2, that's 0 here to -2. That's just that quarter circle, 0 to -2. So we just found the area of that quarter circle. It just happens to be negative because the bottom bound is bigger. So again, it's pi r squared divided by 4, that quarter circle. This will make it that negative, that opposite number to what it is because the bottom bound is smaller. Done. Part B. Find the x coordinate of the point of inflection for g at x. So, to find the point of inflection, we need the second derivative and see where it changes from positive to negative. So what I'm going to be looking for are the turning points of the first derivative. So I'm reminding myself this is the derivative. So concave up means it's increasing. When the derivative is increasing, concave up. It's still increasing, concave up. When does it change from being increasing to decreasing? So at x equals 0, I'm just going to write this down. And where else does it have one? So it's concave up. Now it's concave down. Oh, it changes again here to be concave up. That's at 2. And now it's concave up, and then it changes again, and it's concave down at 3. So we have the answer. Now we're going to write down the word because. And we're explaining that we're looking at increasing to decreasing or decreasing to increasing, and at each one it changes. These are the turning points of the derivative. All right, last part. See how nice 2010 was. They only gave you 3 parts, A, B, C. So in part C, they give you a third function, or second function, h at x, defined with g. And it asks you to find the critical points. And to find the critical points, relative max min means you take the derivative equal to 0. So we're going to take the derivative. So the derivative of g is g prime at x. The derivative of 1/2 x squared. So 2 times a half, subtract 1, make it equal to 0. We're going to add x, and then we're going to solve this looking off the graph. Where is the derivative equal to the x coordinate? Now we're going to think through this a little bit. This one's the trickiest part to think through where they would be. So I'm going to erase this, see if we can figure this out. So again, I'm looking to see where the derivative of g is equal to the x coordinate. Now, the derivative of g is what I'm looking at right now. In other words, the derivative of g is the y coordinate. So I'm looking where on the graph is the x coordinate equal to the y coordinate. So I see up here the x and y are the same number. That means when does the x coordinate equal to the derivative, which is the y coordinate? So 1 is when x equals 3. Is there any other spot in the graph where the x and y coordinate would be the same? So obviously here at -7, -1, all of these values, the x and the y coordinate, are different. But there is one, and here we have a negative and a positive. There is one around here where the x and the y have the same value. But I don't know where that is right there. But how would I find where the x and y coordinate is the same? And this is the tricky part. I need an equation for this semicircle. So if I look at this and try to figure out what is it, so if I plug in x, it has the same y coordinate. I need to know that the equation of a circle is x squared plus y squared equals r squared. That's the equation of a circle. In this case, the radius is 2. So x squared plus y squared equals 2 squared, which is 4. And I want to know when x and y are equal to the same value. So I can actually take out the y and make it x, because I want to know when x and y are the same value, and just solve this equation. So x plus x squared is 2x squared, and then equal to 4, and then solve it. So divide by 2, and then square root, and it's only the positive value on that side. So when x is equal to positive root 2, the x and the y coordinate. In other words, this point right here is positive root 2 and positive root 2, right here. So we have our 2 answers. The second one was really tricky, right? It's going to be okay. Oh, I put the wrong screen on. Here's the right screen. So where is that true? So at x equals 3, and x equals root 2. Equals the y coordinate. So we're looking off the graph. And we used the equation x squared plus y squared equals 4, and then because x equals y, we then solve this equation. We realize when x equals root 2, both the x and the y coordinate are the same number, just like for x equals 3 and y equals 3. So part C was a little tricky. You would have gotten a point for taking the derivative correctly and making it equal to 0, and more points to find 3 and another point to find root 2. So if you didn't find root 2, you'd lose a point, but there's still more points to be had by not giving up in doing calculus and showing what you can do to get points. All right, Mr. G Math over and out. Until next time.